Hello, my dear students. Hello, come to the live classes. Hello. Hello, my dear students. Come to the live classes. Yes, come to the live class, my dear students. Good evening, all of you. My name is Lakshmarana. This is Ellen Brand of Chemistry. Today we are going to discuss remaining topics which are present in the solution chapter, that are colligative properties. So yesterday we have discussed about the colligative properties. What are the colligative properties? So colligative properties, nothing but what? Colligative properties definition we have discussed yesterday, right? So what are the colligative properties? The colligative properties, nothing but the physical properties which are depends on relative number of particles but not nature of particles are called colligative properties. So what are the colligative properties? The physical properties which are depends on a relative number of solute particles but not nature of the particles. Nature of particles, nothing but solute particles, are called colligative properties. This is the definition for colligative properties. So tell me, what are the colligative properties? The physical properties which are depends upon the relative number of solute particles but not nature of the particles are called colligative properties. These are four are present. What are those? Number one, relative lowering vapor pressure. Relative lowering vapor pressure. Then number two, elevation boiling point. Elevation, nothing but increases elevation and boiling point. Then depression in the freezing point. Depression, nothing but decreases. Depression in freezing point. Freezing point. Freezing point. Next, fourth one, osmotic pressure. Osmotic pressure. Yes, look, my dear students. So these are the colligative properties. Whatever the colligative properties are there, all these colligative properties are directly proportional to number of solute particles. Number of solute particles. Nothing but the number of ions. So when it is, so in case all the solute concentrations are given same molarity, the concentration of solution is given same molarity, then at that time it is depends upon the number of particles. In case concentration is given, it is depends upon the concentration of the solute. Sir, in case concentration is same, number of particles also is same, then at that time inversely proportional to the gram molecular weight. That you have to remember is very important. Number of particles are same will be there, then even number of ions will be same, then concentration is same. At that time what we have to do? Gram molecular weight. That is not directly proportional. So at that time gram molecular weight when you are taking, so that is inversely proportional to gram molecular weight you have to take. Okay. All these are the colligative properties. Then one by one we have to discuss each. Yes, one by one we'll discuss. So first one is relative lowering vapor pressure. Relative lowering vapor pressure. So what is the relative lowering vapor pressure? First colligative property, that is relative lowering vapor pressure. Vapor pressure. So simply we call it is RLVP, relative lowering vapor pressure. Sir, what is the relative lowering vapor pressure? Relative lowering vapor pressure ante enti? So we know that vapor pressure, right? So what is the vapor pressure? So first vapor pressure ante enti? So vapor pressure nothing but in case any component is present, the component when it is present in the closed vessel, the vapors will be formed in between the surface of the liquid too, then above the cap what will be there. So the vapors which are accepted by the pressure, that we call vapor pressure. So ikkada form ayye pressure ne manam vapor pressure antunnam. So in case pure liquid is there, a pure liquid is there, that is we call, sir, vapor pressure of pure solvent, that we call, that we represent with a P naught A. So P naught A ante enti? Vapor pressure of pure solvent. Pure solvent. Okay. Sir, ఇదే solvent ki in case if you add B solute, B అనే solute add చేస్తే, then B solute just assume it is non-volatile solute. Non-volatile solute. So non-volatile solute nothing but what I told, man. Non-volatile solute ante em cheppanu? Sir, the solute which cannot evaporate at room temperature, that we call non-volatile solute. For example, for the non-volatile solutes are urea, glucose, then sucrose. All these are non-volatile solutes. Once if you add non-volatile solute, what happens? Solution will be formed. So how the solution will be present, look at. So now in the component, so that is then present in the closed vessel. Here the solution A component is there, then the B component is there. A component is present, then B component is present. We call it is a solution. Sir, whenever the solution will be there, even there also vapors will be formed. Remember, my dear students, this is P naught A, vapor pressure of pure component. Then this is PA, simply we call PA. Then vapor pressure of solution we call. Vapor pressure of solution, that is PA, is always less than that of P naught A. When non-volatile solute is added to the solvent, it happens. PA is less than that of P naught A. PA అంటే ఏంటి? Vapor pressure of solution. P naught A అంటే ఏంటి? Vapor pressure of pure component. సార్ మరి ఎందుకు వేపర్ ప్రెజర్ ఆఫ్ సొల్యూషన్ తగ్గిపోతుంది, ఎందుకు డిక్రీజ్ అవుతుంది అంటే, సార్ ఇక్కడ అబ్జర్వ్ చేస్తే సాల్వెంట్లో మనకు సర్ఫేస్ మీద ఓన్లీ సేమ్ పార్టికల్స్, అంటే ఏ కాంపోనెంట్ అయితే తీసుకున్నామో, ఫర్ ఎగ్జాంపుల్ ఇక్కడ ఏ కాంపోనెంట్ తీసుకున్నాం, ఏ కాంపోనెంట్ పార్టికల్స్ మాత్రమే సర్ఫేస్ మీద ఉంటాయి. ఇఫ్ యూ కమ్ టు ద సొల్యూషన్, ఏ పార్టికల్, బి పార్టికల్, ఏ పార్టికల్, బి పార్టికల్ ఇస్ దర్. బి పార్టికల్ ఏంటి? ఇట్ ఈస్ ఎ నాన్ వోలటైల్ సొల్యూట్ పార్టికల్. నాన్ వోలటైల్ అంటే ఇట్ వోంట్ ఎవాపరేట్ ఎట్ రూమ్ టెంపరేచర్, సో దాట్ విల్ ఆక్యుపై ద లిక్విడ్ సర్ఫేస్, రైట్? సో దీని కింద ఏ కాంపోనెంట్ ఉన్నప్పుడు, it can oppose the vaporization. That is the reason vapor pressure of solution will be decreases. What we call vapor pressure of solution will be decreases. So that is we are calling lowering vapor pressure. దీన్నే మనం ఏమంటున్నాం? లోయరింగ్ వేపర్ ప్రెజర్. సార్ లోయరింగ్ వేపర్ ప్రెజర్ అంటే ఏంటి? లోయరింగ్ వేపర్ ప్రెజర్ నథింగ్ బట్ the difference between vapor pressure of pure solvent to, which is vapor pressure of pure solvent, that is P naught A2. Then vapor pressure of solution. Vapor pressure of solution is what? PA. Then this lowering vapor pressure can be represented with a delta P, that is equals to then P naught A minus PA. P naught A minus PA we call lowering vapor pressure. Then what is the relative lowering vapor pressure? Now it is understand what is the lowering vapor pressure. లోయరింగ్ వేపర్ ప్రెజర్ అంటే ఏం చెప్పుకున్నాం? ఒక సాల్వెంట్కి సొల్యూట్ యాడ్ చేసినప్పుడు వేపర్ ప్రెజర్ ఆఫ్ సొల్యూషన్ తగ్గిపోతుంది. ఎంత తగ్గిపోతుందో ఫైండ్ అవుట్ చేయాలి అంటే, సార్ వేపర్ ప్రెజర్ ఆఫ్ ప్యూర్ సాల్వెంట్లో నుంచి వేపర్ ప్రెజర్ ఆఫ్ సొల్యూషన్ని సబ్స్ట్రాక్ట్ చేస్తే దెన్ లోయరింగ్ వేపర్ ప్రెజర్ వస్తుంది. సో నౌ లోయరింగ్ వేపర్ ప్రెజర్ we got. What is the relative lowering vapor pressure? That we have to find out. First, if you note it, then I will tell what is the relative lowering vapor pressure. Dilip, hi Dilip. Right. So now we have to discuss relative lowering vapor pressure. Now lowering vapor pressure is understand, right? So we'll see what is the relative lowering vapor pressure. We'll see what is the relative lowering vapor pressure. RLVP, relative lowering vapor pressure, means it is the ratio of lowering vapor pressure to vapor pressure of pure solvent. It is the ratio of lowering vapor pressure to vapor pressure of pure solvent, that is P naught A. Lowering vapor pressure is delta P. Delta P, what we are taken? P naught A minus PA. So relative lowering vapor pressure equals to P naught A, sorry, delta P divided by P naught A. Delta P nothing but P naught A minus PA divided by P naught A. P naught A minus PA divided by P naught A. P naught A minus PA is what? Lowering vapor pressure. So it is the ratio of lowering vapor pressure to vapor pressure of pure solvent is called as relative lowering vapor pressure. Clear, my dear students? Right. So now, relative lowering vapor pressure, it is one of the colligative property. Colligative properties are depends upon the number of solute particles, right? So that is what I mentioned here. And experimentally that they are discussed, relative lowering vapor pressure is equals to mole fraction of solute. Mole fraction of solute. What is the mole fraction of solute? XB, that is the mole fraction of solute. Then P naught A minus PA divided by, then P naught A equals to mole fraction of solute. Then we know that what is the mole fraction of solute, man? So mole fraction of solute nothing but number of moles of solute divided by number of moles of solvent plus number of moles of solute. So actually these are the colligative properties that only is applicable for very dilute solutions. So very dilute solution nothing but, sir, here solute, number of solutes are is very less when comparative to number of moles of solvent. So that is the reason in the denominator NB we can neglect. So once if you neglect, then mole fraction of B, you can write it is number of moles of B divided by number of moles of A. So in the place of mole fraction of B, we can write that is number of moles of B divided by number of moles of A. So then number of moles of B nothing but, look at number of moles of B equals to then WB divided by MB. Then number of moles of A nothing but then WA divided by MA. This is the formula. Clear, my dear students? Look at all of you. Observe it carefully. In the place of NB, that we have to take W divided by MB. P naught A minus PA divided by P naught A equals to, then in the place of NB, what we can write? WB divided by MB into then WA, sorry. When it is down to the reverse, then MA divided by WA you can write. So this is the formula to calculate the relative lowering vapor pressure of solute. Then here, sir, in case molar mass of solute, if they will ask a question, sir, molar mass of solute equals to, that is MB equals to, then we can write it is then WB into MA, then divided by WA. So total term, the MB is sent this side, then total term when it is sent that side, then P naught A divided by P naught A minus PA. So this is the formula to calculate the molar mass of solute. Okay. So this is relative lowering vapor pressure. So based on the relative lowering vapor pressure, one of the numerical problem which is given in the previous examination, that we'll discuss now. Then later another colligative properties that we'll discuss. See now. So what are the previous year questions are there? That I will note on the board, which is based on relative lowering vapor pressure. Yeah. At 300 kelvins, at 300 kelvins, 0.06 kg of solvent, kg of organic solute, organic solute is dissolved in 1 kg of water. Observe carefully, my dear students. Observe carefully. So 0.06 kg of organic solute, it is soluble in then 1 liter of water. The vapor pressure of solution, at 300 kelvins temperature is 3.768 kilopascals. If the vapor pressure of water, if the vapor pressure of water at that temperature is 3.78 kilopascals. What is the molar mass of solute? What is the molar mass of solute? So this is the question, man. Then options are given. Then option A 180, then option B 120, then option C 340, then option D they are mentioned it is 260. This is the question based on the relative lowering vapor pressure. Based on the relative lowering vapor pressure, this is the question. So look at the question carefully. Sir, here P naught A minus PA divided by P naught A equals to then WB divided by MB into MA divided by WA. This is the question formula, right? So here in the given data, what will be there? Observe it carefully. Sir, 0.06 kg of organic solute, nothing but what? B. So that you have to take it as WB, weight of solute. 0.06 kgs, nothing but when it is converted into the grams, that you can get 60 grams. How many grams? 60 grams. Then here 1 kg of water solvent is mentioned, that is WA. 1 kg, nothing but how many grams? 1000 grams, that is. Next, vapor pressure of solution, nothing but PA, not P naught A, PA, it is equals to 3.768 kilopascals. Then vapor pressure of pure water 3.78. P naught A, it is equals to 3.78 is mentioned. So now all the values are given. So what we have to find out? Then molar mass of the solute MB you have to find out. Then Ma, how much, sir? Ma is a solvent. So that is the molar mass of water. So molar mass of water is mentioned. We know that that is 18 gram mole inverse, right? Yes. So now molar mass of solute is required means, so Mb equals to then Wb into Ma divided by then Wa into P naught A divided by then P naught A minus Pa. This is the formula. Then Wb, what is there? Wb, what is there? So 60 grams are there into, then Ma, what is there? 18. So 18. Then P naught A, what is there? 3.78 divided by, then Wa, what is there? Sir, 1 kg, nothing but 1000 grams. Sir, into P naught A minus Pa, that you have to calculate. P naught A 13.78 is there. Then this is 13.768 is there. So when it is 10 minus 8, 2, then 7 minus 1, 1, so 7 minus 6, 1, then 7 minus 7, 0, then 0. So 0.012. So here you can get 0.012. So remember, 0.012 we can also write it is, so 12 into 0.012 when it is shifted to here, 10 to the power of minus 3, right? 10 to the power of minus 3. Then, so 3 zeros, then 10 to the power of minus 3, both will be cancelled. Then 12. Then here just take it as this is 0 when it is remove here. Then we can get the point here 37.8 you can get. Then 6 ones, then 6 twos, then 2 ones, 2 nines. Then remaining what will be there? 9 into 37.8 is there. 9 into 37.8 if you multiply, so you can get it is 340. So answer is 340. So 340 is the answer. This is one of the previous year question. So note down the question clearly. Then we'll discuss next colligative property, that is elevation in the boiling point. We'll discuss. So note down the question. Next we have to go for elevation in the boiling point. Second colligative property, elevation in the boiling point. So what is the elevation in the boiling point? Elevation in boiling point. Boiling point that we can represent with delta TB. Elevation in the boiling point we can represent with delta TB. Look, my dear students. So what is the delta TB? What is the elevation in the boiling point? Before going to elevation in the boiling point, one more point I will repeat again. One more point, that is vapor pressure of solution is decreases when non-volatile solute is added to non-volatile solute is added to solvent. So vapor pressure of solution Pa is less than that of P naught A. Is less than that of P naught A. Then if you come to the boiling point, elevation in the boiling point. So before going to discuss in the elevation in the boiling point, you have to remember whenever non-volatile solution is there, in that case, P naught A always greater than that of Pa. Please keep in the mind for all the colligative properties. P naught A is greater than that of Pa. Pa is less than that of P naught A. Clear all of you? Right. So now the boiling point is nothing but, the temperature at which vapor pressure of solution is equals to then atmospheric pressure. Remember, the temperature at which, observe question carefully, observe the point carefully, the temperature at which vapor pressure of component, either solute or solvent, vapor pressure of component is equals to atmospheric pressure is called boiling point. See, look at my dear students. So the temperature at which a temperature దగ్గర అయితే vapor pressure of component, then atmospheric pressure both will be equal. Ante at boiling point what happens, man? Vapor pressure of solution, either component, that is equals to atmospheric pressure, right? Atmospheric pressure. So vapor pressure, atmospheric pressure, both will be equal at boiling point. So observe in the diagram, I will explain that. So this is the vapor pressure of solution. Vapor pressure is there here. The vapor pressure of solution it is. This is Pa, vapor pressure of solution. So outside whatever the pressure is there, atmospheric pressure is there. So that is atmospheric pressure we call. So just assume it atmospheric pressure is 1 atmosphere. 1 atmosphere. At 1 atmosphere, sir, here vapor pressure when temperature increases here, then vapor pressure also increases. We have seen already the graph in between the vapor pressure and temperature. We have seen vapor pressure and temperature. We have seen, sir, it is exponentially increases. I told for any component exponentially increases. So what does it mean? Vapor pressure increases, temperature increases. So boiling point, at which temperature the boiling point, at which temperature vapor pressure of solution equals to atmospheric pressure, that we call boiling point. Clear, my dear students? So now, so remember, wherever the vapor pressure is less, boiling point is more. So that is what boiling point of solution is greater than that of boiling point of pure solvent. Vapor pressure ekkadaithe takku untado, boiling point ekkada ekku untadi. So remember, my dear students, so where the vapor pressure of solution is less, then boiling point of solution nothing but TB. Boiling point of pure solvent nothing but T naught B. Say, look at for the both we are taking. This is the vapor pressure. This is the temperature, right? Temperature in the kelvins. So look at my dear students. So first we are taking graph for vapor pressure of solvent. So we got a curve like this, vapor pressure of solvent. This is for solvent, just assume it. It is a solvent. Then now vapor pressure of solution if you take. Vapor pressure of solution if you take. So I told that vapor pressure of solution is less. Vapor pressure of solution is less. Clear, my dear students? Vapor pressure of solution is less than that of vapor pressure of pure solvent. So less nothing but, so here you can get, so this is for pure solvent. Then here you can get below of this curve, you can get that is vapor pressure of, this is vapor pressure of solution. This is vapor pressure of pure solvent. Vapor pressure of solution. Solution always less than that of P naught here. So now just assume it here at this point, 1 atmospheric pressure is there, that we call atmospheric pressure. At this temperature, at this pressure where the temperature is there, look at. So this is for the solution TB. This is for the T naught B, boiling point of pure solvent. TB is the boiling point of solution. T naught B is the boiling point of pure solvent. This is for solvent. This is for solution. This is for solution. Solution vapor pressure takku untadi. Sir, solution yokka vapor pressure ఏ టెంపరేచర్ దగ్గర అయితే 1 అట్మాస్ఫిరిక్ ప్రెజర్కి ఈక్వల్ ఉంటుందో ఆ టెంపరేచర్నే బాయిలింగ్ పాయింట్ ఆఫ్ సొల్యూషన్ అన్నాం. దెన్ సాల్వెంట్ది కూడా అంతే. సో వేపర్ ప్రెజర్ ఆఫ్ pure solvent at which temperature is equals to atmospheric pressure, that we call boiling point of pure solvent. Now elevation the boiling point means, that is delta TB means the difference between the boiling point of solution to nothing but this difference delta TB we call. So elevation in the boiling point of solution to boiling point of pure solvent is called as elevation in the boiling point. The difference between boiling point of solution to boiling point of pure solvent is called elevation in the boiling point. Elevation in boiling point. Remember, elevation in the boiling point. So note down these graph and as well as whatever the points we are discussed. Kondapalli Krishna Teja said hi. Yes, note down the graph and as well as whatever the points we are discussed, my dear students. So next, the 2 more points we have to discuss in the elevation in the boiling point. Then later we can note one of the previous important question to you people. Clear? Yes. So simply, elevation in the boiling point delta TB equals to T naught B into TB minus T naught B, boiling point of solution to boiling point of pure solvent. Boiling point of pure solvent. Okay, clear? Sir, experimentally they proved that the elevation in the boiling point is directly proportional to molality of solution. Nothing but it is a colligative property. It depends upon the number of particles. It proves that number of particles. So it proves that it is depends upon the number of particles. So that is the reason they will mention a statement, that is elevation in the boiling point. Elevation in boiling point. Elevation in the boiling point, that is delta TB. It is directly proportional to directly proportional to directly proportional to molality of solution. Clear, my dear students? So we can say that delta TB equals to Kb into molality. Delta TB equals to Kb into molality. Clear, my dear students? Sir, in case if you want to get the Kb here, so Kb equals to, so actually, in case if you take the directly proportional, we can say that it is simply delta TB. It is directly proportional to molality. Then delta TB, it is equals to Kb into molality, you can write. So Kb is what, Kb equals to, then molal elevation constant. Molal elevation constant, or one more name we call it is abelioscopic constant. Abelioscopic constant. In case units, if you want to take for the Kb, so Kb it is equals to delta TB divided by molality, right? So delta TB, change in the temperature, that we can take Kelvin divided by molality. Units are mole, Kg inverse, right? Then units we can take Kelvin. So once Kg when it is come, then Kg inverse when it is up, Kg, then moles when it is up, then mole inverse. So these are the units, Kelvin, Kg, mole inverse we can take. Or so we can also take in case temperature is present in the degrees Celsius, then Kg, then mole inverse also we can take. These are the units. So very important, my dear students, for the Kb, that is abelioscopic constant or molal elevation constant. What are the units for molal elevation constant? Sir, what are the units for molal elevation constant? Kelvin, Kg, mole inverse, or degrees Celsius, Kg, mole inverse. Right. So now, so here, then Kb, it is equals to, I told that, delta Tb divided by m. Sir, in case molality equals to 1, you can get Kb equals to delta Tb, right? So based on this, we can say the statement, we can say the definition for Kb, define for the Kb, that is equals to, what is the definition for that, So I will note there here. That is the elevation in boiling point is observed for 1 molal solution, 1 molal solution, 1 molal solution is called molal elevation constant. Molal elevation constant. So what is the molal elevation constant? That is the Kb, that is also called as that is also called as abelioscopic constant. So once again, listen the definition for this, that Kb equals to delta Tb when molality equals to 0, right? When molality equals to 1, right? Molality 1 ఉన్నప్పుడు Kb ఏమవుతుంది? Delta Tb అవుతుంది. So that is what Kb you can define like this. The observed elevation in the boiling point for 1 molar solution is equals to molar elevation constant or abelioscopic constant. So note down these 2 points. Then one more point we have to discuss about it. This, after that we have to take one more problem. Say, look, my dear students, then elevation in the boiling point, how it is derived, actually one more statement is there. Elevation in the boiling point is directly proportional to molality. We have discussed that. Not only for the molality, elevation in the boiling point is also directly proportional to lowering vapor pressure, is also directly proportional to lowering vapor pressure. Then here from the Raoult's law, delta Tb, remember, delta Tb, it is equals to Kb into mole fraction of solute. So it is from Raoult's law. Then according to thermodynamic laws, Kb, it is equals to R into T naught square divided by change in the enthalpy of vaporization. Change in the enthalpy of vaporization. Remember, Kb nothing but Kb ante థర్మోడైనమిక్స్ నుంచి డెరైవ్ చేసింది ఇది. థర్మోడైనమిక్స్ నుంచి అన్ని కాన్స్టెంట్స్ ని బేస్ చేసుకొని దెన్ ఇది ఈ కాన్స్టెంట్ అనేది డెరైవ్ చేశారు. సో దట్ ఈస్ ఆర్ ఇంటూ T naught, R nothing but ideal gas constant, T nothing but T naught nothing but boiling point of pure solvent, then delta H VAP nothing but enthalpy, change in the enthalpy of vaporization. So we can substitute the Kb in this case. Then delta Tb, it is equals to, in the place of Kb when it is substitute, then R into T naught square divided by delta H VAP, that is enthalpy of vaporization, into then molar mass of solute. Sir, molar mass of solute nothing but in the previous what we have discussed. So look at my dear students, molar mass of solute equals to what we have discussed, the number of moles of solute divided by, then directly you can take the number of moles of solvent, because it is very dilute solutions. In the denominator we can neglect the number of moles of solute. So number of moles of solute nothing but Wb divided by Mb. The number of moles of solvent nothing but Wa divided by, sir, Ma. What is that? Number of moles of solvent equals to weight of solvent divided by molecular weight of solvent. Number of moles of solute nothing but weight of solute divided by molecular weight of solute. So in the place of Xb we can substitute all these things. So delta Tb, it is equals to R into T naught square divided by change in the enthalpy of vaporization into Sir, NB divided by NA. So why again we should write NB? So in the place of NB, we can write that is WB divided by MB, right? So into then MA divided by WA. So remember, sir, here enthalpy of vaporization nothing but latent heat of vaporization into 1000. So look at enthalpy of vaporization delta HVAP, enthalpy of vaporization equals to latent heat of vaporization into then molar mass of solvent, that you must be know this is formula. So in the place of enthalpy of vaporization, in case if you want to take, so from this we can get it is, so 1 divided by latent heat of vaporization equals to then molar mass of solvent divided by, sir, enthalpy of vaporization we can take. So remember, my dear students, molar mass of solvent nothing but MA only. Molar mass of solvent ante malli మీరు ఏదో అనుకున్నారు, MAనే molar mass of solvent, right? So in the place of molar mass of solvent, sir, if you take molar mass of solvent divided by enthalpy of vaporization, what is this? Delta VAP, enthalpy of vaporization. Molar mass of solvent divided by enthalpy of vaporization. In the place of these two terms, we can take 1 divided by latent heat of vaporization. So note down that then delta TB, it is equals to R into T naught square divided by, sir, in the place of these two terms, we can write it is latent heat of vaporization into, then still what will be there? WB, clear, my dear students? WB divided by MB into 1 divided by WA. 1 divided by WA. Sir, here in case molar mass of solvent is present in the grams, then we have to convert into the kgs, because here one's kg there, then we can take it is right. So finally we got it is, so in the place of this, we can substitute delta TB equals to, that is I told KB, the KB. So latent heat of vaporization, in the place of latent heat of vaporization, what we can take? The enthalpy of vaporization, what we can take? Then molar mass. So molar mass divided by, that is, so this is totally KB. So KB into, then molality you can take. KB into molality you can take. Clear? This is KB, this is molality. Weight of solute divided by molecular weight of solute into 1 divided by then weight of solvent in the kgs. Weight of solvent in the kgs. ఎప్పుడైతే దాన్ని kgs లో మనం తీసుకున్నామో, then we have to take in the place of this here, then divided by 1000. So into 1000 you have to take. Clear, my dear students? Understand? So the same formula, in case in the form of this, if you take, that is KB equals to RT naught square divided by, then latent heat of vaporization, nothing but what I told. So molar mass of solvent, that is MA, divided by then enthalpy of vaporization, then into 1000. Enthalpy of vaporization into 1000. This is actual formula for calculate KB. KB ni calculate cheyadaniki formula enti? KB equals to then R into T naught square into MA divided by, sir, delta H vaporization into 1000. Sir, what is the R in this case? R ante enti ikkada? R equals to ideal gas constant. Ideal gas constant em తీసుకుంటాం? 8.314 joules mole inverse Kelvin inverse. Then delta H vaporization. So it is joules we can take. So delta H VAP nothing but change in the enthalpy of vaporization. Change in enthalpy. Enthalpy of vaporization. Vaporization. Then remaining MA is there. MA is molar mass of solvent. Clear, my dear students? So this is the formula for KB and this is the formula for delta TB. Now we will discuss one of the problem based on it. So based on elevation in the boiling point, we are discussed some of the formulas. Finally we got it is delta TB equals to KB into molality. Remember, molality nothing but so WB divided by MB into 1 divided by WA, or in case if it is there in the grams, then WB divided by MB into 1000 divided by WA. So in the place of M, we can substitute this. Delta TB equals to the KB into WB into 1000 divided by then MB into WA. So remember, whatever the terms are there, I will discuss here. The KB equals to molal elevation constant. Then WB nothing but weight of solute. Sir, MB nothing but molar mass of solute or molecular weight of solute. Then WA nothing but weight of solvent, right? So remaining delta TB is there. Delta TB nothing but that is elevation in the boiling point. These are the terms. So based on this formula, we can calculate then one of the previous year question. That is here, before going to that, even the KB also what we are discussing, the KB equals to R into T naught square into molar mass of solvent divided by delta HVAP into 1000. Sir, in case here latent heat of vaporization, if you want to take molar mass divided by solvent, then enthalpy of vaporization it won't come. That is the KB equals to, in terms of latent heat of vaporization, R T naught square into molar mass need not to take, then divided by latent heat of vaporization into 1000. In terms of latent heat of vaporization, molar mass need not to take. Why? Because what is the reason? 1 divided by latent heat of vaporization equals to then molar mass divided by delta HVAP, nothing but enthalpy, change in the enthalpy of vaporization. Clear, my dear students? Understand? Yes. Based on the all constants, we got the formula like this. Now we'll see the question. Yes, my dear students. You have only one question we'll discuss based on it. So because time is over, then the remaining questions tomorrow we'll discuss. TF, then TB, freezing point, Freezing point, boiling point. Where are the boiling point question? Yeah. Yes, my dear students. Tomorrow we'll discuss the problems based on it. Molar elevation constant as well as elevation in the boiling point and as well as depression in the freezing point also. Thank you. Thank you for all. We'll see later. Tomorrow we'll discuss. The time is over. So already near to the 10 o'clock, right? Okay, students. Bye. Bye, bye, bye. See you. Bye.